Okay, so thank you very much, Simon, for the introduction. And it's nice to be here at the institution. And I'm going to tell you all about some work we've been doing on the testing and analysis of the world's first metal 3D printed bridge. So I'm going to start with a sort of general introduction about 3D printing and the different methods, and then talking about testing of the bridge at different levels. So we've been looking at the material, some components of the bridge, and we've tested both of these to destruction, and then testing of the full bridge itself. And I'll finish off with some conclusions. So 3D printing or additive manufacturing can generally be defined as the process of making a physical object from a 3D digital model, typically by the fusion or deposition of successive layers of material. It's one of the fastest growing methods of manufacture. You can print almost any geometry, and the range of applications and the potential is huge. So the concept of 3D printing dates back some time. There's many processes with many names, and there's a degree of standardization now. You can print a wide range of materials, but it's really only been the last 5 or 10 years where 3D printing has come into its prime. It's now a lot more cost effective, a lot more accurate, and a lot more accessible than it was. So in engineering, it's the aerospace and biomedical industries that have taken up the technology most rapidly. So in aerospace, it's a big driver is making your structure as light as possible and also minimizing waste. In bioengineering, compatibility and customization are obvious big benefits you can get. The uptake of technology in construction tends to be a little bit slower than some other industries, but there are already some early examples of applications, some optimized joints. There's been some construction-focused research, but I think there's a huge amount of further opportunities for 3D printing in construction. So methods. So there's quite a wide range of metal 3D printing techniques, but the ones that are most suited to construction, and construction is very large in terms of its scale, are powder bed fusion and another method called directed energy deposition. And I'm going to say a word about the two of these. So for powder bed fusion, the input material is metal powder. It's selectively fused together using a laser or an electron beam. The powder has to be housed within a chamber, which creates an inert atmosphere, and that limits the maximum size of the components. It's quite a slow process, powder bed fusion, but it's very accurate. So it's suited for relatively small but quite intricate elements. We've done some initial testing on small structural sections that have been produced by powder bed fusion. We've tested some square hollow sections of different local slendernesses and looked at their structural response. And then the second method is directed energy deposition, and this can either be powder-based or wire-based. So powder-based directed energy deposition uses a laser or an electron beam as the power source again. The powder is fed in to the beam through a nozzle. You can achieve very good dimensional accuracy, and it's a lot quicker than powder bed fusion, but it's still a relatively slow process. And then directed energy deposition, but wire-based. So this time the input material is wire. The rates of deposition are much higher than powder-based. The wire is much, much lower cost than the powder. And wire-based directed energy deposition, which uses an electric arc as the heat source, is called wire and arc additive manufacturing. This has by far the best acronym, WAM. And this is the method that was used to create the bridge that I'm going to be talking about. It's essentially an adapted welding process. The structure is formed entirely from weld material. Maximum dimensions are essentially unlimited. And deposition rates of up to about 10 kilograms per hour per robot can be achieved. Dimensional accuracy is reasonable, and there's potential for this to improve with better control with time. So what are the opportunities that 3D printing can bring, and also what are the challenges? Well, thinking generally about the opportunities, greater structural efficiency, reduction in material consumption, reduction in wastage, streamlining and speeding up the design build process, enhanced customization and architectural freedom, potential for improved accuracy and safety, potential for reduced construction times, environmental advantages, and potential for reduced labour requirements. So they're the kind of general things that may be possible with 3D printing. And then thinking more specifically, so geometric freedom. You can put the material where you want it. This is how our concrete friends choose to exploit geometric freedom. They could make any shape they wanted, and they came out with that. And this is how we do it in the steel world. For me, a little bit more elegant. There's scope for highly optimized elements. So these are examples of connection nodes. So Arup redesigned the original lighting node, which is shown on the left-hand side. They undertook topology and manufacturing optimization. And the final node, which is on the right of the three images, was 75% lighter, so a quarter of the weight of the original node. When they built it, it still cost 3 times as much as the original one, but the costs are reducing quite rapidly with time. Things like tapered elements, curved elements, details like stiffeners, shear keys, openings, all of these features require additional operations, which means time and cost, with standard manufacturing. But with 3D printing, it really doesn't make any difference whether you have these features or not. They can be easily accommodated with no real penalty. Optimization doesn't have to be just in terms of geometry either. You can also tailor the distribution of your mechanical properties to the demands. For example, you could use higher strength material at the midspan of members, where you've got maximum bending moments, but lower strength and higher ductility material towards the connection regions, where you need that extra ductility. There's potential for energy absorbing materials like engineered materials as well, which can be 3D printed. Residual stresses are often part of the metal 3D printing process. And residual stresses generally have a negative influence on the structural resistance. But with 3D printing, the sequence in which you build up the structure is such that you do have some control over the thermal stresses that get locked into your structure. And so potentially you can think of, instead of residual stresses being negative, think of pre-stressing your members against any subsequent applied loading. An example of that would be, this is a conventional eye section which has been welded at the flange to web junction, and that puts the tips of the flanges in compression. And in terms of your minor axis buckling resistance, that compression reduces your capacity. If you 3D print the section and you 3D print the tips last, that will leave them in residual tension, and that could potentially enhance the flexural buckling resistance. And we already see this effect in conventionally welded eye sections which have flame-cut plates, which give you these tensile residual stresses at the at the flange tips. I think additive manufacturing is likely to complement rather than replace conventional production. It's quite hard to imagine something more efficient than eye sections and tubular sections being produced by hot rolling and cold forming. To me, that wouldn't generally be sensible to use 3D printing for. It might change. But the idea of using hot rolled bits for the members, but then 3D printing for the connection details, that would start to make more sense. And there's also opportunities for strengthening and repairing existing structures. And overall, the ability to put material where you need it in the optimal configuration to resist the applied load, potentially to tailor the material properties to meet the stress and ductility demands, brings clear opportunities for reducing material use and reducing waste in construction. So there are sort of potential opportunities. There are obviously challenges. So cost, though some methods are relatively low cost. I think a big issue is the process and product variability. We've got well-established standards, quality control processes, statistics for normal steel. We don't have this for 3D printed material, and we might never have it because of the inherent variability of the process. And we might need to be thinking more in terms of standardizing and doing our quality control processes on products rather than materials. The geometric freedom brings greater challenges. Having nice standardized sections does make life a bit easier, so the freedom brings challenges. And ultimately, of course, if we're using this to construct buildings, structures, bridges, we need to make sure that they're safe. Okay, so that's a bit of sort of background generally to the topic. Now I'm going to talk about the bridge, so the MX3D bridge. So MX3D is a company based in Amsterdam, and they have built the world's first metal 3D printed bridge. We've been working alongside them from the start of the printing process on the testing, simulation and verification of the structure. So the bridge is 10.5 metres span, about 2.5 metres wide. It's got a complicated geometry and unusual surface finish. And it will be placed in the centre of Amsterdam in the Netherlands next year. The technology used to print the bridge is MIG welding in conjunction with a robotic arm. The robots can print 4 kilograms of material per hour, and the 3D printed part of the bridge was just over 4 tons. So it's about 1,000 printing hours, which is about 5 weeks full time. The actual printing process was spread over a longer period because there was various points of testing throughout the build process. The bridge is printed from austenitic stainless steel wire. And this is the process that's used. So a welding torch controlled by a robotic welding arm, controlled to follow a prescribed path and build up the structure layer by layer entirely from weld material. So you can't open up Eurocode 3 and expect to find much applicable to the bridge, so we had to think slightly differently how we're going to verify the safety of this structure. Greater emphasis on advanced analysis, inspection, and ultimately load testing of the final structure. So for the bridge, Arup were the structural engineers. We initially did some material testing of the bridge, and then component testing, so parts of the bridge to failure, full testing of the bridge, and this was done in a number of stages, finite element modelling. A fatigue analysis was carried out by Arup, and the bridge is fitted with various sensors which will be used to monitor the bridge throughout its life in real time. Okay, so material testing first. So we wanted to know what are the basic material stress strain characteristics. So we carried out a series of tensile coupon tests. And we cut coupons from material printed in the same way as the bridge. And we cut the coupons at different angles to the weld layer direction. So we cut coupons out at 0, 45 and 90 degrees to the layering direction. We also wanted to see, we wanted to test the material both in the sort of as-built condition, where you had the undulating surface, but also the sort of raw material, the smoothed down material. So we milled the as-built undulating geometry down to get a flat surface, and then we took coupons from the flat material, so-called machined coupons, and also from the as-built material. The coupons were sprayed with a speckle pattern prior to testing, and this gave us features for what's called a digital image correlation system to track during testing. So digital image correlation is a non-contact measurement system. Basically, digital cameras are used to take photographs of the specimens at regular intervals. Software is then used to track the movement of the dots in successive images, and these shifts that it detects are displacements, which can then be converted into strains. And this measurement technique is particularly useful for 3D printed material because the strain tends to be less uniform than ordinary produced material. So we were able to get strain output, and we did indeed see that you have this sort of banding effect and an underlying directionality to the material properties. And you see some of this in conventionally produced material, but it's more pronounced for 3D printed material. So looking at the stress strain curves, in the 0 and 90 degree directions, we found, so this is for the machined material, we found that the Young's modulus was about 25% lower than conventional stainless steel of this grade, whilst in the 45 degree direction we found that the stiffness was actually slightly higher than the normal 200,000 newtons per millimetre squared. In terms of strength and ductility, the material performed well, so good ductility, similar to ordinary produced material. And this shows you some of the values. So Young's modulus down to about 130,000 and up to about 230,000 newtons per millimetre squared. In terms of the strengths, these are typical strengths that you would expect for this grade of material: 350 to 400 newtons per millimetre squared, 30 to 40% strain at ultimate strength. So why did we have this variability in Young's modulus in particular? We went to speak to our friends in the materials department, and they said that you can investigate this using a method called electron backscatter diffraction. You can look at the microstructure of the material, and what we found is that the grains were preferentially orientated following the heat path that is generated in the 3D printing process, and that was able to explain the stiffer response in that 45 degree direction. So having looked at the material properties of the machined coupons, we then looked at what does the surface undulations, the as-built material, because the bridge was left as it was printed. We had these surface undulations remaining, so we wanted to see what do they do to their performance. So this table shows you the ratio of the key material properties in the as-built condition, so the undulating geometry, relative to the machined coupons. And you can see that generally the key mechanical properties are about 10 to 20% worse than the machined material. So that's the effect of this geometric undulation. But ductility was more severely affected, particularly for the coupons that were tested at 90 degrees to the printing direction, because you're sort of pulling across the largest undulations and across the weak points between the successive layers. And you could see that clearly in the failed specimens. So these are pairs of coupons before and after testing. You can see the fracture in the middle of the coupons. The 0 degree directions, where you're sort of pulling in line with the printing direction, they're the most ductile, whereas the 90 degree ones, where you're pulling across the layers, they were the least ductile. Okay, so that's the material properties. We then looked at bits of the bridge, so component testing. We printed a series of square and circular hollow sections for testing in initially compression, and we still have some bending tests to do. So these are the specimens having been machined flat on the ends and cleaned. And the specimens were chosen to sort of match key parts of the bridge, so at the base and at the top of the handrail. Because of the geometric variation, it's not so easy to actually get an accurate measure of the real geometry of these things. So you can't just do normal geometric measurements using calipers and so on. So we used 3D laser scanning in order to capture the geometric profile. Now, unfortunately, most of the bridge is tubular, and it's not so easy to scan the inside of tubes. So we scanned the outside, and then we created molds of the inside by pouring in this silicon, let it set, and then pulled it out. It sounded really easy, but we had some real trouble getting some of those these molds out. They all came out eventually, not all in one piece, but generally good. We then scanned the silicon casting, and then we merged the outer and inner scans to get a full 3D model of the specimens. And once you've got that, you can then look at the geometry in quite close detail. So you can get information about the variation in wall thickness, diameter, and so on. And of course, 3D printed material is more variable in its geometry than conventionally produced material. This enabled us to capture how much that variation was. So we then carried out a series of tests. So these are compression tests for square hollow sections. And generally speaking, their failure mode was similar to what we would normally expect. So this is local buckling with the alternate faces buckling inwards and outwards. This is what you would normally see. But we did see, when we looked at the 3D laser scan models, that failure initiated at the points of higher imperfections or thinner material in those models. And if we look at the normalized resistance, so vertical axis of this graph is the ultimate load we achieved in these compression tests, normalized by the yield load, or squash load, area times yield strength, plotted against the local slenderness of the cross-section. So class 4 sections would be moving towards the right-hand side. And then I've just got some existing test data here, mainly on conventionally produced stainless steel. And you get a reducing normalized capacity with increasing slenderness because local buckling is becoming more pronounced. And then here are the results for the 3D printed material. So it's a similar trend, reducing normalized capacity with increasing slenderness, but it is clearly a bit lower than the existing data, reflecting the higher imperfections and so on. And we would need some sort of lower bound in order to think about design of these things. But by and large, the components behaved in a similar way to conventionally produced material. So moving on to the full bridge. So we tested the bridge at various stages of construction in a total of 4 visits. The first visit was when 2 meters of the bridge had been printed. we took some fairly rudimentary equipment to Amsterdam, and so things like car jacks and winches, and loaded the first part of the bridge to see how it behaved and compare it to a finite element model that we'd developed. And the agreement was pretty good, and we were comfortable that the bridge was doing roughly what it was supposed to, and so printing continued. We then visited in July 2018 and tested the bridge without a deck in place. So you can see the members making up the sort of lower part of the bridge. And then the third visit, there was a stainless steel deck welded in place. And that third visit was September last year, and we called that the serviceability testing, because we applied load levels up to what a designer would be using for serviceability design loading of that footbridge. The fourth visit was very recent, just a couple of months ago, and that was the ultimate limit state testing, which I'm going to explain in a minute. So the first visit we went with some heavy suitcases. The second visit involved a transit van and some equipment. The third visit involved a very full van, more equipment, and the fourth visit involved even more equipment, all taken over by train to the Netherlands, and all of the equipment was then used to test the bridge. So we carried out both horizontal loading on the handrails to simulate pedestrians pushing on the handrails, and also vertical loading. So vertical loading was initially achieved through water tanks. So we had a series of water tanks, 1 meter cubed, so 1 ton of loading per tank, and we loaded them up as evenly as possible. So this was July 2018. It was during the World Cup, that's why the England flag is there, showing our support. And in total, the bridge deflected about 14 millimetres under the 4 tons of loading, and that was roughly what we predicted using our finite element simulations. So in the next step, the deck was welded in place. So this is a view from on top of the bridge, and you can see the continuous stainless steel deck there. And the total loading this time was applied up to about 10 tons, and it was through a combination of water tanks and concrete blocks. So 10 tons of loading, roughly corresponding to the serviceability design load on the structure, and the bridge deflected about 25 millimetres. We also had some parallel finite element modelling of the structure. We used the material properties that we'd measured on the coupons as input into the models, and we were able to simulate a number of load cases, the same as what you would apply to a conventional bridge design. So various load combinations, and we looked at its behaviour. The serviceability testing and the finite element modelling enabled the bridge to be opened for the first time to the public, but in a sort of controlled way. So not so controlled that no one was allowed on it, as it appears in this photo. This was taken nice and early in the morning before everyone arrived. But it was open to the public for 1 week at something called Dutch Design Week in 2018. So this is a view from our drone above the bridge. And then people were allowed on the bridge in a sort of controlled fashion. We asked the chap who was supposed to be controlling the number of people to keep it to 20. And there was at least 50 on at one stage. And we weren't too worried because the loading that we'd applied was quite a lot higher. But then people started jumping up and down. So we became slightly worried. And what was nice is that people were genuinely very interested in the structure. They were very engaged, asking lots of questions, which I think is all great for structural engineering. So this was one of the jumping groups, and well, if there's any sound on this thing, we'll hear in a minute there was a slightly disturbing noise towards the end of their jumping, but it turned out to be a dropped item by someone, nothing more sinister. So let's see if these people, yeah. We weren't laughing at the time, but then it turned out to be okay. Okay, so that was Dutch Design Week. It was open to the public for 1 week, and before it can be open to the public in a sort of uncontrolled fashion, the next step was to do ultimate limit state load testing. So this was done just a couple of months ago, and we applied load using a combination of these concrete slabs and water tanks. So initially what we did is we applied 4 levels of these concrete blocks. That corresponded to just under 10 tons of loading, and we were putting these on manually, one by one, in a controlled sort of organised pattern so that we kept the loading approximately uniformly distributed. So we were on the bridge at that stage, so we didn't want to be at loads that were higher than we'd been to before. So we then at that stage, we put some water tanks on, and we increased the load by a further 5 tons. We then took the water off again and put the final 2 layers of blocks in place. That then took us up to a load level which was still below what we'd had with the water in place. And then we put the water tanks back on and took up to the full ultimate limit state design loading, but without us being on the bridge at the time. We put some students on the bridge because we weren't so worried about them. So I've got a time-lapse video which shows how this process worked. So that's us putting the layers on the bridge in a sort of organised fashion, layer by layer, trying to keep it evenly distributed. Then the water tanks were put on and filled up. That took us up to about 15 tons. And then we went back down again with the water. 2 further layers of bricks, water tanks back on, and then up to the ultimate limit state design load, which was close to 20 tons. We then, at a slightly reduced vertical load level, we also applied some horizontal loading. And these were done using these props with hydraulic jacks attached. And so we jacked the bridge in and we pushed it out. And then we took everything off very quickly. And finished. So you'd think it might be quite interesting testing, the world's first metal 3D printed bridge, but there was something even more interesting. So this is a live video taken at the time of the test. Let's see if...
Okay, people, I'm now reporting live from the ultimate limit state test of the MX 3D bridge. You'll notice that there's no one else here, despite it being a crucial stage of the testing. That's because something more interesting is happening outside. A forklift truck has got stuck in the mud again, and we're going to have to tow it out using that. That man there is responsible for getting stuck again.
So we had a team photo, of course. So this was not when the full load was on the bridge, but a bit lower. So a few people that I should thank. So this is me. This is Craig, who's a colleague at Imperial. He did a lot of the planning and organisation of the testing. We have Melody, who's here, and Nicholas, who are both pretty close to the front row here. And Gordon's a technician at Imperial, and for sure it wouldn't have been possible without him. He had a lot of the ingenuity and know-how. Testing in a tent in the middle of nowhere is not so easy, and it does bring some restrictions. So it needed a bit of ingenuity to actually apply the loads that we wanted to, and take the recordings that we wanted to. You'll see that the bridge has a nice sort of pattern here. This is a speckled pattern for the DIC system, the digital cameras, to pick up. So those dots were placed manually using a board marker basically on the bridge. So that was, I managed to avoid that task myself, but there were some willing people to help. So the total testing, it lasted almost 3 weeks. So although the video was quite speeded up, the whole process took a long time, preparing, testing, taking everything away. So when we finally said goodbye to the bridge, it was highly emotional, as you can imagine, so we had to say goodnight. But very good fun. So, a few conclusions, what we've sort of learnt from this process so far. So the use of metal 3D printing is growing across many sectors. For construction, it seems that these two methods, powder bed fusion and directed energy deposition, are the most suitable, particularly considering the scale of construction. The MX 3D bridge is great because it gives you an insight into what can be done, and it's due to be fully open to the public next year. I think 3D printing is a fantastic opportunity for us as structural engineers, researchers and practitioners to apply our knowledge to the sort of range of geometries and materials that 3D printing allows. I think it's a real opportunity for all of the different parts of the steel construction sector, from designers to researchers with fabricators and so on, all included. And there's still a lot of questions and there's still many challenges, but that's what makes it all interesting and exciting. And with that, I'd like to finish. Thank you very much.